Let's continue on with our next problem. This says the rate at which a baby bird gains weight is proportional to the difference between its adult's weight and current weight. They have gone ahead and given us the differential equation that represents that. And you can see they've even solved for the constant for us. So we can start out with that equation. And it says let B of t be the solution to this differential equation with this initial condition. The baby bird was born weighing 20 grams. Is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Okay. So let's just check this out and see what we can get here. We know when the baby or the bird weighs 40 grams, we're just going to substitute in here dB dt equals 1/5 of 100 minus 40, and that's going to give us 1/5 of 60, which should be 12. Let's check when the bird weighs 70 grams. dB dt will equal 1/5 of 100 minus 70, or 1/5 of 30, which will be 6. Show the work to explain your reasoning. You can see that our reason, we would go with the bird gaining faster is at 40 grams. As a matter of fact, it's actually growing twice as fast at 40 grams than it is at 70 grams. Next one says use separation of variables to find a particular solution or the particular solution based upon our initial conditions. Okay? So first things first, we need to separate our variables. I need to get the b on this side and the t on that side. This has already been factored for us, so they're making our job pretty easy on this one. So let's divide by 100 minus b and multiply by dt. Once we get to this step, we have our variables separated. We can take our antiderivative. Antiderivative, be careful, we have a chain rule on this. So yes, this will be the natural log of the absolute value of 1 minus b, but think about the derivative of the inside here. That's going to give us a negative. That's going to equal 1/5 of c, or excuse me, x, plus our buddy c. As we've been making a habit of, when we're given our initial conditions, we go ahead and as quickly as possible, go ahead and substitute in to solve for those. So this will give us negative natural log of 100 minus 20 equals 1/5 x, which is 0, plus c. So c is simply just going to be negative natural log of 100 minus 20, or 80. That's our c value, which means we can go on from here with these two. Negative natural log of 100 minus b will equal 1/5 of x minus the natural log of 80. Okay. I think I probably just noticed here, I changed from t to x's. So I'm going to go back in and fix that real quickly, since that doesn't match the problem that we're doing. Okay, so let's go ahead and manipulate this a little bit to get my equation, my b of t in this case. So I'm going to change my signs. Natural log of 100 minus b equals negative 1/5 of t plus the natural log of 80. When we take everything to the power of e, this will be one absolute value of 100 minus b equals negative, e to the negative 1/5 of t plus, remember what this is going to be, it's going to be an exponent. So that means this would be an e, I'll go ahead and write it, times e to the natural log of 80. Okay. And then we can add a little plus or minus in front of this. 100 minus b equals e to the negative 1/5 of t times, let's think what happens with that. Isn't that just going to be 80? Okay. And go ahead and subtract 100 from both sides and change the sign, so this is a positive b. I'll kind of do all those in one step. So this is plus or minus 80 e to the negative 1/5 of t plus 100. Again, I changed the sign, and my positive and negative here have kind of switched around. I do need to check to see which one of these will match my condition here. And you'll see when t equals 0, I've kind of run out of room here. In order for me to get this to be 20, this is going to have to be a negative. So b equals negative 80 e to the negative 1/5 t plus 100 is the particular solution to this problem. Okay. Let's go ahead and take a look at our next problem. And it talks about a bacteria in a certain culture increases at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, how many hours will the number of bacteria triple? So you can see this describes that example of directly proportional to the amount, which is going to be our P equals C to the E, or E to the KT. Okay? So to go ahead and find the solution to this, we can say at the beginning, let's just say P sub 0, we have a population of P. If we are going to double that, or I'll call it P1, maybe that makes it lit. And then we know we're looking to find at 3 hours, P of 3 will have double that amount. Okay? So I can go ahead and substitute in here. Of course, if this is the original amount, that means that C equals whatever that initial population would be. And I can substitute all this in, and this will be when we are doubling our population, that initial population will be E, and we know that occurred when T was 3. I can quickly just divide both sides by the P, and I'll have 2 equals E to the 3 times, oops, this should be a K, times K. Take the natural log of both sides. The natural log of 2 will equal 3K, which means K will equal 1/3 the natural log of 2. Okay. In how many hours will the number of bacteria triple? Well, we can go back in here. Now that we know K, I'm going to rewrite it over here to say P is going to equal the initial amount, P sub 1, E to the 1/3 natural log of 2 times T. And let's go ahead and kind of do the same thing we did over here. When we triple, we're looking for that time, and when we triple, this should be 3 times the initial P1 will equal P1 E to the 1/3 natural log of 2 times T. We're solving for that T. Divide both sides by the P1. This gives us 3 equals E to the 1/3 natural log of 2 times T. If we take the natural log of both sides, this will be the natural log of 3 equals, when we take the natural log, this just drops down to, or becomes, 1/3 the natural log of 2 times T. And T would equal, We're going to divide both sides. Dividing by this fraction of 1/3 would be the same thing as multiplying by 3. 3, natural log of 3, divided by the natural log of 2. And our units here would be in hours. Let's go ahead and take a look at our next problem. And this says during chemical reaction, the function is given by y equals f of t, models the substance present in grams, and at the start of the reaction we have 10 grams of the substance, okay? And it's modeled by this differential equation. First thing it says is let's just go ahead and use a tangent line to approximate the amount of the substance after t